So my talk today will be about recurrent networks and trying to figure out what can be the next thing and some ideas. I will try to explain possibly the recent success of the recurrent networks, what is like the big mystery of this long short-term memory that many people are asking about, and how to make some simple extensions of simple recurrent networks to be able to better memory. And then I will try to figure out like what are the limitations of the recurrent networks and what is the possible way how to overcome these limitations. And in the end, I will also discuss some like long-term research plan that some of us have at Facebook research group, how we can possibly develop machines that will be able to really understand the language, just like maybe the most exciting goal for many of us who do research in NLP and machine learning. So to see like the trajectory where we are going, I think it's good to have like some very brief overview what happened and what were like the main breaking points in the history. Like the recurrent networks are known for like a long time. They became popular in the 80s and 90s in the work of Jeff Ellman and Jeff Hinton and Mike Jordan and so on. There was actually a lot of famous researchers working with recurrent nets back then. Because maybe because the main idea is very attractive to reuse parameters over time and model like sequences with some very simple architecture. Like it usually looks something like this in the old papers. For example, from Jeff Ellman, there's basically just some input layer that represents the current feature, and there's a hidden layer that does some nonlinear computation that also sees its own previous state from the previous time step, and then there's the output layer. So the recurrence is the whole magic of this model that allows the model to create some kind of memory which is represented by the state of the hidden layer. So this is like very simple model, and people are very excited about like what it could possibly learn because there were like very interesting experiments done by Jeff Ellman, for example, in his famous paper, Finding Structure in Time. Well, the excitement didn't last that long because soon several research groups that figure out that there are some problems with training the recurrent networks, and maybe there was some slight overstatement about the drawbacks. For like almost 20 years, the recurrent networks were in general considered to be not possible to be trained by stochastic gradient descent and backpropagation through time because of the vanishing and exploding gradient problems. So that was a little bit disappointing that there was so little work on RNNs for like pretty much 20 years. There was, of course, several groups, mainly I would say ETSIA in Switzerland, that was working actually still on the RNNs even in times where nobody else was, considering them as successful models. They developed the LSTM recurrent network architecture that is now very popular, and I will try to explain a little bit the magic behind LSTM later. And then when I did get to RNNs myself, it was actually very easy to start beating benchmarks across many data sets. When I did visit GHU, I was able to get like quickly the best results in language modeling, speech recognition, machine translation, data compression, even on like very strong systems from commercial companies like IBM. So this was pretty exciting that very simple models suddenly started to work. And I did publish the code to like allow other people to work with these techniques. And looking back, I would say that the main trick that actually wasn't really known before, and that is now part of pretty much every implementation that I know for recurrent networks, was to prevent the instability of the training, which was known to be happening before, but people didn't really know the cause and the solution. The solution seems to be very trivial, or at least a simple one, to just not allow the weights to change too quickly, for example, by throwing away problematic parts of the updates of the weights, or clip the gradients so they don't start exploding, which is a very rare problem, but it has very catastrophic consequences. So that's basically for it. And then the recurrent nets were becoming more and more popular and accessible through machine learning toolkits. Like I did name here like 3 of them that were getting started around like 2010, like PyBrain and Tiano Torch, but there are of course many others that are getting published almost every month these days from commercial companies like Google and Facebook and Microsoft and others as well. So today, recurrent networks are applied actually to many problems, like speech recognition, machine translation, many NLP applications, and then plenty of other use cases are being investigated, like to model videos and to recognize handwriting or predict the user intent, and pretty much we can use recurrent networks for almost any sequential problem, and they usually work very well, even without much tweaking, so that makes them very attractive. The downside maybe is that, as I was saying, like 20 years people did discard recurrent networks because of like some theoretical reasons that these models may be difficult to train, and basically people were too pessimistic. Now maybe people are getting a bit too optimistic, and they actually expect from RNNs sometimes too much. I think that they are not the end of the story. And if we want to, for example, build some intelligent language models that would really understand the content of the language and be able to like scale to artificial intelligence, then I think that we still have to do a lot of work, and I will get to these problems in the second part of my talk to basically highlight what I think are the next thing we should be focusing on the research side. And of course, there are like the reasons why the complicated architectures are preferred, because there's like a pressure at the conferences. It's easier to get papers published if people use very fancy, complex techniques. So I think that's a little bit unlucky. There's maybe too much hype these days. So to maybe slightly reduce the hype about recurrent networks, I will try to explain what is going on when it comes to the longer short-term memory, which is pretty much the point of the LSTM architecture from Etsia. That's quite complicated. It's using a very complex model of neurons that have input gates, output gates, and forget gates. And I will show that for language modeling, we can actually get the same effect from much simpler model. It's published in this paper that we published last year at iClear. It's called Learning Longer Memory in Recurrent Neural Networks. So back to the basic architecture, oh, I see some symbols are shown incorrectly here, but that should be okay. Don't worry. So there's this input layer, hidden layer with the recurrent connections, and the output layer and the corresponding matrices, where the recurrent matrix is the R symbol here in the picture. This is the simpler recurrent network. It's known that if we will try to train this model to represent memory in the state of the hidden layer, that it will focus more on the short-term patterns, and it will form just kind of like short-term memory that's not going to last for long. It's caused pretty much because the gradients vanish quite quickly, like after 5 or 10 steps that we propagate the gradient through time, they become usually like very, very close to zero. So the idea, again, the equations are a little bit screwed up, sorry for that. On my laptop it was looking okay. So the equations basically say that if we want to obtain the state of the hidden layer, it's basically some simple activation function that is applied to matrix multiplication times the input vector plus matrix R times the previous state of the hidden layer. The activation function is some simple sigmoid, and then there is a softmax usually at the output layer to perform the classification. So that is pretty much, I think, the only equations that I have in the slides, which should be better. And as I said, this simple architecture have the problems that were studied by Seb Hochreiter and Yoshua Bengio in the early 90s. It was known that the gradients when training this model can have some serious problems. They can either vanish or explode. Mostly people that actually focus on the vanishing gradient problem, which prevents the networks to learn the longer short-term memory. On the other hand, as I said, like there was this crucial problem with the exploding gradients, which actually was the real reason why people were failing to train the RNNs on larger data sets, why the training was unstable, and looking back, it's like a very simple hack to clip the gradients, and that was able to make the training stable. So I think that it's actually very interesting that often like the ideas that are very impactful are very simple at the same time. For the vanishing gradients, the story is a little bit more complicated, but I will soon show a simple trick how to make the network to remember longer memory in a kind of explicit way. Many people did think that this problem of the vanishing gradients is actually a problem of stochastic gradient descent algorithm, but it seems that pretty much every solution that actually works and that is able to find longer memory in like solutions that represent longer memory into recurrent networks is more like on the side of modification of the architecture. So we can still use SGD, and it doesn't seem to be a problem of SGD. It seems to be more like that the architecture of simpler recurrent network, of the LMR architecture, doesn't really encourage the network to form the memory. So the idea how to form this longer memory is actually, again, something that you would find in very old papers, like from Mike Jordan and Mike Moser that write several papers about this architecture in the late 80s. It's an idea where the matrix, the recurrent matrix, wouldn't be fully connected, so that each neuron doesn't see all the neurons, all the states of the neurons from the previous time step, but each neuron would be connected through recurrent connections only to itself in the previous time step. It's like a very simple structural constraint on the matrix. Of course, this network would have much less parameters, and it's actually weaker, mostly, almost always, I would say, than the LMR network. But what we can do is actually combine both ideas together and have a single recurrent network that has two hidden layers, where one is the element type hidden layer that is like fully connected, and the second one is the hidden layer from Moser's models that has basically just the self-connection for the neurons. So instead of having full recurrent matrix that is dense, we have for this Moser's hidden layer, we have just single parameter per hidden neuron for the recurrent connections. It can be seen as a diagonal recurrent matrix. And that is here denoted as the alpha, because we can even for the next experience we can keep this self connection to be fixed at a value that is close to 1, so that it will explicitly tell the network to keep its longer memory in this second hidden layer, and so that it will be changing slowly. Also, there is no activation function in the Moser's linear recurrent layer. The alpha value, of course, can be learned, like the self-recurrent weight for the neurons in the Moser's layer. For simplicity, we did keep it fixed at 0.95 to really like show explicitly that this is kind of like a very simple like weighted combination of the input features that has exponential decay in time, which is coming pretty much exactly from this definition. And then there is the connection, so that the slowly changing hidden layer is connected also to the quickly changing one through the matrix P, which helps a bit by a few % in perplexity in the results that I will show soon. We did decide to call this model structurally constrained recurrent network, which is a little bit long name, but it pretty much describes exactly what the model is about, because if we have a code that implements the simple recurrent network, then we can actually obtain the SCRN models by simply putting hard zeros into parts of the recurrent matrix, plus a few more details, like not having activation function for this part of the hidden layer, and then adjusting also the learning rates correctly for this part, and that's pretty much all that needs to be done. So we didn't really need any gating mechanism. We didn't need pretty much all the number of parameters that otherwise people would find in LSTM that have difficult explanation what they do. Alternative name for us was like slow recurrent networks because there is this part that is changing slowly, but that seems to suggest that the model is slow, which is actually the other way around. Because it's so simple, it's actually more efficient to be trained on like large data sets. For the results, I will show like perplexity results on language modeling, which is like very standard way how to evaluate these recurrent networks. One will be the pen tree bank, which is quite well known. The other one is more highlighting the importance of the longer short-term memory, which is text8. That's basically Wikipedia data, and there it's clear that that being able to understand, to remember the names seen in the recent history is actually helping the perplexity a lot. It's also interesting for people who know language modeling. It's interesting to see the relation between what used to be done for like this type of patterns in the statistical language modeling community since the early 90s. People did actually develop models called cache models, which are complementary to the baseline Ngram models. The cache models basically just build some very simple model from the recent history of, say, last 100 words. So it's like adaptive part of the language model, and that gets interplayed with the probabilities given by Ngrams. So it's super simple, but this is very much what the LSTMs are doing for language modeling tasks as well. So the explanation of their like success can be actually super simple. We did also publish the code for this model, so people should be able to easily reproduce the results. I think this code is part of Torch, I believe. It was written by Sumit Chopra, who is co-author of the paper. For the language modeling results, here's basically the perplexity for different models. Perplexity is like the measure of precision of the language models. The lower, the better. So we can see that we can get like 10% gain from the cache model when it's used together with the Ngram. So this is like very, very traditional old techniques. And then there is the simple recurrent network with 100 hidden units. It's already better than Ngram and like at 129 perplexity. Then if we use LSTM with the same size of the hidden layer, with the trick that each neuron in LSTM layer is actually having 4 times more parameters than the simple recurrent network because it has all these gates, then we get similar gain as from the cache model, which is again about 10%. And then from the structurally constrained recurrent network, we can get pretty much the same gain by having 40 these slowly changing units. So this is like some empirical evidence that these models really model cache for the SCR, and it's actually very explicitly defined as a cache model. And for the LSTM, it seems like it's just doing the same thing. Of course, we can't really make much conclusions based on one experiment. We did actually more of the experiments. That's why we did choose the text8 dataset, which is like 17 million words from Wikipedia. The effect from cache is much stronger there because there's like wider variety of the model of the topics. And we can see that actually cache is helping Ngram's models quite a lot, like 25% reduction of perplexity following 309 to 229. The simple recurrent network is already quite a bit better than Ngram here. And LSTM beats the simple recurrent network by quite a bit margin, like by 50 points in perplexity. SCR actually, even if it has actually less parameters than LSTM, is even better than that. So that's again like some kind of empirical evidence that when we see data where cache is much more important than LSTM and SCR, and it's actually giving us quite a big improvement over the simple recurrent network. So again, like there's some correlation between the gains from cache and the gains from LSTM and SCR and over simple recurrent network. Of course, this is like with kind of small models because we did inflate the size of the training set to 17 million words and still have just 100 units. So we can get to larger models with 500 units. All the recurrent networks get quite a bit better. Still, we can see nice gains from the models that can model the cache. LSTM is actually even a few % better than our SCRN model. That's interesting. I think that with more tuning, we'll be able to get similar results. But the main message here is anyways that if we have very large amounts of data, then the recurrent nets that we train are always limited when it comes to the size of the hidden layers. So we did take it as like very positive results that we can match the results of much more complicated models with something that has less parameters and can be trained more quickly. So for the discussion of the results, well, the SCRN model, if we keep the self-connection fixed at 0.9, it explicitly accumulates a weighted combination of the input features, so it can be seen as weighted backwards with some exponential decay. Empirically, LSTM, performance of LSTM correlates very strongly both with the cache model and with the SCRN model. So I hope that this is giving like people insight what the LSTM models actually learn in language modeling and machine translation tasks, basically for all these NLP tasks. And for very large data sets, I would say the positive message is that we have this model that actually is simpler than LSTM, and it's much cheaper to train, so that we can train either bigger model or a model on more data. So for conclusion, like this is like the first part of the talk. The conclusion is that with simple tricks, we did see that we can kind of at least partially overcome the problems that are caused by the vanishing and exploding gradients. The exploding gradients can be mostly solved by some simple techniques that, for example, clip the gradients, and the vanishing gradient can be kind of, again, not completely solved, but made more or less significant by choosing slightly different architectures of the recurrent networks. We also can see that the LSTM actually doesn't really form any kind of long-term memory, which I think some people would like to see, and it would be great, but for that we would probably need to develop some different models that's more like for future research. It seems that if we want to have long-term memory, the model itself should be able to grow in size, so I will get to that back at the second part of this talk, where I will introduce in the end a model that can actually grow in size with the complexity of the patterns that are seen in the test data. So what can we do to go like beyond the recurrent networks and beyond the deep learning? What are like the other things what these models cannot learn and that could be learned possibly with something else? Well, there are actually very simple examples, again, like people that realized this already in the 90s, and now we are like pushing this direction forward. There are like higher level concepts like being able to memorize variable length sequence of symbols, which may sound trivial to people, and I will be showing examples later that it really is not like difficult concept to understand, but the models that cannot model computation but can mostly perform just clustering of sequences, which is more or less what RNNs and LSTMs do, then these models really struggle with generalization in cases where the pattern is of some algorithmic nature. That's why we call these patterns algorithmic patterns. Again, there's some small mistakes in how the slides are shown. So the patterns shown here are supposed to be A and Bn patterns, like A power n, B power n. People who did have some computer science classes probably know that it is like context-free pattern that cannot be described with finite machines, and we will see that the recurrent networks struggle to understand this pattern. And actually LSTM, because they can count, they can still solve the A and Bn, but then we can just slightly increase the complexity and require the models to memorize sequences with variable length, and there we already can break LSTM very easily and still are able to design a model that can solve memorization and even like addition of binary numbers from examples. Of course, like people can be wondering, like we have like these nice language modeling results, then we see some of these kind of like algorithmic patterns that are somewhat artificial. So we can like design plenty of tasks where we can break some models, but which one are actually the ones that we should be focusing on to basically move forward to artificial intelligence? Well, we were like thinking of it for quite some time, and we did write a whole paper about it. It's going to be the second part of my talk. Paper is called Roadmap Towards Machine Intelligence, where we try to kind of like turn around the approach a bit. So instead of trying to find the simplest patterns that break our models and then try to solve them, because that may be not completely convincing, because it's kind of not showing the real goal, what we want to achieve. We first defined what we would like to do, how the artificial intelligence should look like, and then we need to think like, how can we get there? So the ultimate goal for artificial intelligence, in our opinion, in opinion of several of us from Facebook, is AI that will be based around communication. Like, one can definitely make like all kinds of models that could be considered as artificially intelligent. Some can be based, for example, around behavior. So it can be a machine that can, for example, play StarCraft or some computer game very well, or it can be some other machine doing some arbitrary tasks. But it seems that if we want to have useful artificial intelligence, then it should be really doing things that require communication. We need to be able to basically set the goals for the machine, and it needs to be able to explain us the result that it is able to obtain. So just some examples that I have here, like truly artificial intelligent machine should be able to, for example, help students to understand homeworks better. So basically help all the people, like in the schools, like millions of people spent years of their life at schools trying to understand plenty of topics, and if they would have like some private teacher that can help them to understand things better, we would like optimize the society in a great way. The same way we can we could be using communication-based AI for like helping researchers to find relevant information, scientists to solve like very complex tasks, computer programmers to really not write programs manually anymore, but rather asking the computer to do something for us in natural language, so we would not need the artificial programming languages anymore. So that's like the biggest goals that we could think of, that we at the same time think are actually doable, so no traveling in time or anything like that. So for the roadmap, of course, there's like plenty of things that we could consider, but then that would be quite difficult to see any direction. So while defining the roadmap, we tried to pick a minimal set of components that will be truly required to be part of the intelligent machine, because we believe that that we can't really discard them, and everything that can be discarded we didn't include into the roadmap. And then we also like discuss in the paper how possibly the machine can be constructed, but it's still far away. So for the components, as I said, like the ability to communicate seems to be completely necessary. We have intelligent machine that cannot communicate with us, then basically we can't really ask it to do anything, and it can't basically produce anything meaningful to us. We can maybe observe its behavior, but that doesn't seem very useful. So really the ability to communicate seems to be like necessary for our plan. Then the motivation component is necessary because we don't just want to communicate with the machine, we actually want it to be able to do something useful for us. So it should be possible to share basically our goals with the machine so that it can accomplish tasks for us. And then there are the learning skills, like of course, like now it's maybe becoming more obvious, but a long time ago people did believe that maybe the intelligent machine can be pretty much programmed by rule-based approaches, and we believe that it should be based as much on learning as possible, which will require all kinds of further components that I will be talking about later, like long-term memory and being basically able to learn, how to modify itself and adapt to new problems. So the component of the framework, now we did already have to make some more concrete choices. We did decide to go for simulated environments because we can't develop the intelligent machine in the real world. It would take too long because there's plenty of problems that we have to deal with if we would go into robotics. So we rather prefer the simulated environments because their experiments are much more easily reproducible and can be simulated much faster, and it's in general much more convenient. Then we have other components are the rewards and communication channels that are necessary for the communication and the motivation parts. And then we believe that a big part of successful learning is the incremental hierarchical structure of our understanding. So the environment has to include some very simple tasks that may look trivial to us, but it can help the machine to basically get the prior knowledge about the general problem-solving skills. So instead of like jumping directly into some complex task, we'll be starting actually with some very simple ones. We believe that we didn't actually find any good set of tasks that would be useful for like teaching the machine the communication skills. So it seems that we have to develop this data set ourselves. Also, like it doesn't seem to be easy task at all. Like if we would be adding complexity to this environment too quickly, then even like intelligent machine, in the same way as intelligent human can fail to learn, like even like humans are limited in their learning abilities. If there's too much complexity coming too quickly, then we basically fail. It's like trying to skip the elementary school and going directly to the university. Like people who don't know how to read would basically have no idea to catch up. So the complexity has to increase kind of at the right speed, like especially because the machine doesn't have any prior knowledge. Then we believe that we have to put there a lot of simple tasks in the beginning. And at the same time, we would be adding the complexity too slowly. Then maybe we would observe what happened like in the last 20 years. For example, the NLP community that set its goals to like solve, say, parsing and part-speech tagging. And these tasks themselves are maybe interesting tasks, but they are supposed to be part of like a bigger machine that understand the language, and that actually never happened. People did spend years and years by trying to improve accuracy of the parsers, and it's not very clear where that was going and still is. So we have to be also like challenging in asking the machine to do like more complex tasks and not stay with some artificial tasks for too long. So for the high-level description of the environment, I will show in a few slides a picture that will maybe explain it better. But for now, we have a learner, which stands for the intelligent machine. It's basically the set of algorithms that does the learning. And then there's a teacher that is in the place of humans. It's basically setting goals to the learner, and it's using rewards to motivate learner to behave in some way. Later, the teacher can be replaced by, or will be replaced by human who will be setting the goals. And of course, like for scaling up, which is really far away, I would say, we can consider like real input signals coming from internet, so that it can be also made part of the communication channels. And so on. Like we discuss these issues more in detail in the paper, although I think it's still quite far away. So for the simulated environment, we have like three entities there. One is the environment, as I said, which is like a simple script-based reactive agent that produces some signals for the learner that are very simple. It represents basically the simulated world. Then there is the learner, that's the intelligent machine that has as its objective function to maximize the average incoming reward, at least in the beginning of its life. We would like to make it as much unsupervised as possible. So maybe later it doesn't need to have much supervision at all, but in the beginning of its life, basically, the goal for learner is to maximize the sparse reward that is coming from the teacher. And and the teacher specifies the tasks for learner. In the beginning, it's based on the on some scripts, and later to be replaced by humans. So communication works in a very simple way. We have like the learner has input channel. It receives the information from the environment and from the teacher in form of some simple sentences in some very simple language, and it produces also output that influences its own behavior in the environment. So if the learner wants to, for example, walk somewhere, then it will just pretty much say this command to the environment, and it will execute it. And then the rewards are also part of the input-output channels. So this like a simple visualization, like with 2D world with some objects and the learner that has access to information what is in front of him, and then it can learn like from the examples to perform some basic commands. So here it's already assumed that it already does understand basic tasks. So there is the input channel part and the output channel part. So the teacher specifies a task, move and look, and then the learner is able to remember this command for which it needs memory. It executes a command when it addresses the environment. It says I move, then the environment performs the command for the learner. It moves forward. The environment confirms that the learner did successfully moved by saying it. Then there's follow-up conversation. The learner says I look, and then it basically receives the reward because it did accomplish the task specified by the teacher correctly. Of course, this may look very trivial in the first place, but we want to encode as little prior knowledge in the system, so that it has to discover basically pretty much everything, how to form the memory and how to parse the incoming signals, how to produce the instructions to the environment, and so on. And as I said, the goal is to maximize the incoming reward, which means that the learner has to be able to accomplish the tasks as quickly as possible. So it's quite different to what is currently the mainstream in reinforcement learning, when people really like try to simulate millions of trials or runs in some simulated environments, for example, some simpler computer games, and while providing pretty much dense reward to the system, we are like rather thinking that if we want to obtain some intelligent machine that will be scalable, it has to be made as unsupervised as possible from its own beginning. It has to be part of its early design. Otherwise, the solutions will simply not scale. So it's like a big part of our plan. So the learners have to be fast. They have to be very efficient about the data, the amount of data they see before they can accomplish the tasks, and that is pretty much the goal for the learner, to maximize the incoming reward. So that means to do as little simulation steps as is possible to correctly solve the task. Also, it's very easy that if we specify the tasks through language, it's very easy to build like some incremental structure, because we can be demanding, or the teacher can be demanding like combinations of tasks, and the machine really has to be able to figure out new names for new types of actions, and that really would require it to learn incrementally, which again, to humans it sounds very simple, but that's exactly where models like, say, recurrent networks would be already failing. For adding up humans, I think that's quite far away, and if we can get to the point that the learner can really learn from a few examples how to use new verbs and how to use new words, then there will be really like amazing success. But of course, it's we have to also finish like how this plan will scale up later, so the humans can replace the teacher and basically start specifying the goals to the learner through the communication channels. And of course, in very distant future, once we would have this pre-trained learner that has basic communication skills and the learning skills, then we can just ship these intelligent machines to like real people who would be teaching them to perform tasks that would be specific to them. Adding real-world signals also doesn't seem difficult because we can just make everything part of the communication channels. The learner can we can teach it to form a query in its output channel that would be sent to internet, for example, to some search engine, get the resulting page back, and then it can read it again at its input channel. So this is like a very language-focused plan, but it seems that it will be sufficient to develop the intelligence. So I was saying already several times that the recurrent networks will have problems to scale to very simple problems, like the understanding of the algorithmic patterns. So in a few slides I will present this paper called Inferring Algorithmic Patterns with Stack Augmented Recurrent Networks, where I will show that actually, again, some small modification of recurrent networks allows us to learn some simple computation. It's definitely not the solution to AI, but at least it's interesting to know about it. And for the scalability, which is really like a big part of, I would say, any reasonable plan how to solve artificial intelligence, we think that there has to be some ways how the intelligent machine can deal with some problems or do some tasks. And in general, we can say that we would like to see possibility of the computation model the intelligent machine will be based on to have capability to form long-term memory, which, as I said before, this is something that recurrent networks do not really have in a strict sense. Also, the model should be complete in a Turing complete sense. That is, there should be a finite length description of any regularity in the data. People can definitely deal with this. Human languages are Turing complete. We should also not limit the AI in any way, because otherwise it's probably going to fail to be as intelligent as we are. Then we also think that successful intelligent learning will have to be incremental in some ways, so that before solving complex tasks, it should be much easier to solve it if we first can solve some subtasks. So we even plan to design our environment and the tasks that the teacher is specifying in such a way that the learner can develop some simple skills first and build on top of these skills later. And as I was saying before, learning from small number of examples is also crucial. This is pretty much the objective function, to minimize the number of examples that the learner has to see before it can acquire a new skill. And that's also related to decreasing amount of supervision. We as people have very little supervision coming in a form of reinforcement signal, and we can still learn in a very unsupervised way. And it seems that AI will have to be based around similar concepts. So for the paper, that's actually showing how we can learn some simple computation with recurrent networks. Again, the ideas can be found in very old papers. Like in the 80s, 90s, people they were already aware of these computational limitations of the machine learning models, so they did try to overcome them by adding some topological memories to recurrent networks. We can just choose the most simple one, which would be a stack or several stacks that the recurrent network learns to control. So the model still looks very much like a recurrent network, and in fact it actually is a recurrent network with some special connectivity in the recurrent matrix, as it's more explained in detail in the paper. Here basically in the picture we can see that the hidden layer is deciding what action will be performed on the stack. It's basically a softmax over three functionalities. Either it can decide to push a value that is also learned by the hidden layer, but what value should be written on top of the stack, or it can remove the topmost value from the stack, or it can decide to do no operation. The full model is explained in the paper. It's it's represented by completely differentiable architecture. So everything is trained again by SGD. Of course, we can put there different topological memories, like it doesn't have to be stacks. It can be, for example, tapes or lists and so on. We consider several of them in the paper. Here are the algorithmic patterns that we consider that require counting. These actually are solvable with LSTMs because any model that has a linear layer can learn to count basically if you have A and B and pattern, and if you have a neuron that can do something like +1, -1, then it will be able to count. So this is still something that actually, these patterns that motivate people to develop the LSTM model in the first place in the 90s. They wanted to actually learn like patterns of this type, like these simple grammars. Here the examples are showing in bold the letters that are predictable. So if there is, for example, the AN, BN pattern, then we can see that if we see 2 A's and 1 B, then we can predict deterministically the two next incoming symbols, which is BA, because we already know there are 2 A's and that there needs to be 2 B's and 1 A. Then we measure precision on predicting these predictable characters, and pretty much all the models that we would consider to be able to model this pattern solve these problems, like LSTMs and the stack RNNs. The recurrent networks just are able to memorize the pattern seen in the training set, in the test set, because we test the models on much longer sequences than the models were did see during the training. Then the recurrent network, because it's realized just memorization just doesn't do it. And then we have like this simple extension of these tasks to something that would break even LSTM. That's the sequence memorization. And the binary addition, where we show the network 2 numbers in written binary, and then the result of summing them together or adding them together. So it's quite a tricky algorithm that has to be discovered from examples that I think many people would struggle with to discover in purely unsupervised way by just predicting what is the next character. And still, like, surprisingly, the model was actually able to do it with SGD and some weak form of search. So here we can see that there are basically there is this input sequence, and there is the prediction sequence that is outputted by the model, or that's basically what the model thinks will be the next character. Of course, it cannot predict anything in the stochastic part of the sequence, but when there is the result part, it actually does everything correctly, and for that it actually has to perform quite complex functionality and switch between several states. So once it's reading the first number, it's writing it in 3 stacks. It's writing the information, not the number exactly, so it can actually write everything in opposite. Then it switches after it sees the plus sign to storing the second number. The green color means push operation on the stack. Here we have 10 stacks, and the number in the squares means what is currently on the top of the stack. And then the red color means pop, which is used in the last phase, in the last state, where the result is produced. It's actually in the reverse order, because that's much easier for the stacks. And we can see that basically the expected functionality is shown here, like that the stacks are like popping the values from their tops. And then there is this special functionality learned by stack number 5, which is the carry functionality, which is needed to correctly add the numbers. So it's quite interesting that the model was able to learn it in just without any supervision, just through predicting the next symbol in the sequence. Of course, it sees like thousands of sequences during training, but we don't really say to it like what each symbol means and what it should be doing with each stack, which used to be done in the 80s, 90s. So for the summary of this part, there are definitely like interesting things, like the model that I just described. If it can operate with 2 or more stacks, it's already Turing complete, so it already can represent any computation. We were able to demonstrate that it can learn algorithmic patterns. What I was showing is reproducible because the code is public. It has some form, the stack RNNs have some form of long-term memory, so that definitely they can store something in the stacks that is not really modified or accessed for possibly very long time. And we were able to learn some simple problems that would otherwise break the recurrent networks and the LSTMs. Of course, looking at this from the perspective of the intelligent machines, we are still like far from having a good solution, because we did use the long-term memory only to store the partial computation inside of, for example, this binary addition. By the algorithm itself, the functionality is learned in the weight matrices of the recurrent network, so that this model is not really suitable for some kind of incremental learning. If you would teach the model to do binary addition, then to do binary subtraction, and then want to train it some other task that would use these 2 functionalities as basically subcomponents, then it would actually not work well. So there's definitely like something that we want to do better in the future. Also, all of the stacks do not seem to be very general choice for the topology of the memory. As I said, like in our toy tasks, we did consider like a friendly representation of the problem, so the memorization is done in the reversed order and so on. Of course, we can choose to use, for example, tapes, and then we could solve the memorization in the arbitrary order, but even tapes seem to be not very general choice for the memory. Like computers, like modern computers, are not really Turing machines. They are Turing complete, but they are not Turing machines, and there are some reasons for it, which is the computational efficiency. So there's definitely a lot of questions that we still have for ourselves, like what to do next to be able to learn like these simple patterns, and of course to explain fully the relation to the previous roadmap to machine intelligence, like the patterns, like the memorization and so on. That's pretty much what the learner has to learn in the environment in the first place, to be able to repeat some commands that the teacher specifies, and to repeat the commands from a few examples, and not through like brute force memorization from many training examples. We would really need to be able to express this kind of computation. So it seems that natural languages are, in a opinion of some of us, quite related to the algorithmic learning. So for the conclusion, to achieve true artificial intelligence in the future, which is what we are trying to aim for, we believe that we need to set a truly AI complete goal, like something that would be really ambitious, and not, for example, some chess playing machine or something. Then we need a new set of tasks, because there are no tasks currently that would allow us to make progress in this direction. And I was describing how the tasks may look like. Then we need to develop new techniques. As I was saying, like recurrent networks are great, but they are like very simple things that they cannot do, and they have a lot of limitations that we have to overcome. And then, of course, it's great if more people would realize what we are trying to do and would help us to achieve the goals. So that's it. Okay, thanks.
Thanks a lot.
My question is about all this gradient vanishing and exploding. If you take your constrained structured recurrent networks, have you observed that this vanishing gradient effect is in some case less than in standard networks, so this model in some sense more correct?
Yeah, definitely. You can observe it by, for example, looking what is the magnitude of the gradient vector as you propagate it through time. So in the normal recurrent networks, as I was showing in the slides, after like 5 or times steps back through time, the gradients are close to 0. But if you have this structurally constrained recurrent network, because you have these self-connections that are close to 1, then the gradients have to be propagated actually many more time steps, like maybe 50, 60 time steps back, because they are still significant after like 10, 20 steps. So yeah, we observe it.
Okay, thank you.
Please.
Hi, hello. Thank you for the talk. My question is about your vision of building AI. So, as you said, we as humans receive relatively small amount of supervised rewards as we live, and still we are very intelligent. So, my question is, what is the place of unsupervised learning in your vision of how do we achieve AI? Don't you think that we may need not a convenient set of tasks such as prediction, I don't know, language modeling, summation and so on, not that kind of algorithm tasks, but rather something that can really test the ability to learn in a supervised way? Maybe some self-motivation schemes, not just that simple simulators.
Yeah, well, definitely when thinking about the supervised, semi-supervised, or unsupervised learning, you can think that if you have completely unsupervised learning techniques, then that would be more like a machine intelligence that is not really optimized to do anything specific. That would be probably hard to build artificial intelligence around such objective. If you think about purely supervised training, as we have, for example, the classifiers that we are building now, that it's completely unrealistic because nobody's going to give the machine basically right answers all the time, so that it can basically learn how to navigate in the real world. It seems that humans learn definitely with some weak supervision that kind of helps us to develop some understanding of the world, but later we probably set the goals more or less for ourselves, so we kind of create our own goals based on what we did learn as children, and we set us our beliefs about the world. So that's definitely important to consider. So I'm on the side of a very weakly supervised learning through just some sparse rewards.
Any more questions?
Actually got 3 questions.
Or maybe just ask one by one, or I will forget them.
Коллеги, прошу вставать, пожалуйста, если можно, чтобы вас видела камера, потому что мы транслируем онлайн. Спасибо.
First, very simple questions. Did you compare your results from the first part with some GRU-based networks, which is like recent addition to LSTM-based models?
GRU networks were also developed for the same purpose, to basically remove the unnecessary complexity of the LSTMs, and they basically just keep the gating mechanism that also allows to form this longer memory. So again, the trick they learn is very similar. We did actually publish these works in the same month, like Montreal and the Facebook group. So we were not aware of each other until we did present this work, of course, later at ICRE conference. So of course we could have compared these models, but I'm pretty sure that the conclusions would still hold that the GRU will do this very similar thing as LSTM, and plus minus few percent the same as the SCRN as well.
Thank you. Second, more abstract question. Back in 60s and 70s, even before those years that you told about, very biologically inspired models were popular, with Hebbian learning, with spiky neurons and all that stuff. Do you believe that those things are not needed to implement your intelligent agent, or so?
Yeah, well, it's a difficult question. Who can say? Basically, until we build artificial intelligence, we will not really be able to point out on the right direction. My own opinion is that we don't really need to copy everything from the brain to develop artificial intelligence. Maybe it would take too long because it's very difficult to actually understand what the brain is doing. And from what I've seen, the neuroscience is usually explaining, after the machine learning people discover some algorithm, then the neuroscientists are explaining how it's possibly implemented in the brain, which I think is more it would be great if it would be the other way around, that the neuroscientists would actually come with the ideas that would work for us and not just explain later what happened. So some argument why I think that maybe more this computer science-based approach, when I was talking about the computational limitations of the models, that's the motivation for me. Why I think it can be good. If you look at the airplanes, they also don't have to flap the wings, and they can actually fly. So we don't have to actually copy everything exactly to get the desired effect.
Okay, and my last question, actually, more practical one. can you suggest several like relatively short projects that people could work on, like a month-long project that could be beneficial to anyone?
Yeah, we are thinking of something like that. So let's see if we will be able to put together something. As I was saying, like it seems that having some environment that would allow you to basically generate kind of the patterns where the machine is supposed to learn the structure and maximize the rewards, that would be like very useful, because right now if people want to work on like some new techniques that would possibly be able to scale to machine intelligence, like there's no such data set. You can pick like entry bank language modeling, but you know, like that's not gonna scale to AI. There's some motivation and so on. Or you can pick like ImageNet, but that's just about classification again. Like it's not AI complete. Maybe you can pick some Atari games playing, but again, like as this project is defined, then you can just brute force it with like huge number of computers, and you are going to beat other approaches even without developing new techniques. So I think that it would be like amazingly important for the future AI research if we would be able to publish kind of like this simple environment that can be used to measure like the success on our like way forward, and we definitely want to do it in the future.
Okay, thank you.
The question from Twitter from people who are watching us online: how one can smartly choose the clipping range to handle the problem of exploding gradients?
Smartly choose.
How one can smartly choose the clipping range to handle the problem of exploding gradients.
Yeah, well, I did treat it basically as a hyperparameter, so I did choose it by basically looking at the empirical results. In my opinion, in my experience, it wasn't that sensitive to the exact value. Basically, the main point was to not allow the gradients to become like exponentially larger than they should be. So if one wants to be maybe more clever than setting some hard threshold, then maybe the solution could be like saying that the norm of the gradient should not be, say, like 10 times bigger than is the average norm of the gradient or something like that. But I don't think it would have like a big impact on the results.
Thanks.
There were a series of works, for example, by Ilya Sutskever, about the learning with the methods of the second order methods for teaching recurrent nets. Are these methods as efficient as it was stated?
As efficient as what?
As it was stated.
Well, in my opinion, definitely not. In Ilya's opinion, maybe yes. Actually, when he did publish his paper in 2011 on like character-based language modeling, because actually at the time I had several years of experience with that, I was interested in comparing like SGD with his session free. So we did write immediately after that a paper together, which I have on my website. You can send me email if you want. I can send you a link. It was called Subword Language Modeling with Neural Networks, and there you actually can see that when we compared SGD training for RNNs with Hessian-free and all these multiplicative connections and whatever tricks that Ilya used, then the performance was pretty much the same. And in fact, for this problem, very simple models that were based on logistic aggregation and engram features were actually even better. So I myself was never a big fan of the Hessian-free, and I think that the claims were overstated, but again, like, it would be the best to ask Ilya about it.
Thank you. And one more question, more practical one. How do you tune your hyperparameters, and how do you expect how much data would you need to train your models?
How much what?
How much data would you need to train your models?
Well, usually the more data, the better. And when it comes to the hyperparameters, that's maybe the other way around. Like, I think that if you can get rid of the hyperparameters, then it's always good. Of course, you can start adding some unnecessary hyperparameters that's improving your perplexity by 1% here and there, but usually in my work I try to remove the components that didn't seem to be crucial. So in the end, in the recurrent networks, like you had like very few hyperparameters. You had the learning rate, where I was using some schedule based on the performance on the holdout data, so it didn't have to be tuned at all. and pretty much the only thing that the user had to specify was the size of the hidden layer, where again the bigger was better, and it was just more computationally complex. So there was actually quite almost nothing to be tuned. You just had to decide how much time do you want to wait for the model to be trained, and otherwise I didn't have to tune anything, maybe also because I was using some prior experience, but I'm sure it would be possible to write some short algorithm that you would just tell it how much data do you have and how long do you want to wait, and it would choose the optimal value for the hidden layer size and the number of classes automatically.
So I guess we can take one more question. Yeah. So.
Thanks for very interesting talk. I have a question about AI, about true AI, which can write a book or understand the laws of nature or maybe flirt with girls. Do you believe that such AI is achievable in current machine learning paradigm?
In what?
Current machine learning paradigm.
In current machine learning paradigm.
Yeah. So it's just a matter of CPU numbers and neural network topology or something like this, and we.
Yeah, well.
Do you believe in this?
That's actually what that roadmap paper is about. Like in large part, we are actually claiming that we have to do quite pretty much everything else differently. Like even like basic things that are like taken as granted these days. Like for example, division of the data into training set and held out sets and test sets. Like we don't actually want to this to be part of intelligence. Basically, everything should be training and test data at the same time. The machine should be just reading the data and minimizing the time that it needs to achieve good performance. So in several things, we are actually thinking about like redefining a little bit like how the machine learning is trying to achieve the artificial intelligence. If you ask about like the possible limitations of the CPUs, like of course like we know that the brain is very much like a parallel computational model, while the computers are like serial computational models, and of course we can simulate each other.
You can simulate parallel in CPU, of course.
Well, I think that the AI should be probably based on the parallel model because it seems more natural for us for understanding. Like we can have like we can do things in parallel and so on, and of course you can simulate this with serial architecture as well. So these are kind of like difficult questions that I don't have like any like definite answer for. Like for now, I would be more like in favor of the parallel architectures, which we can simulate still on the serial computers. That's pretty much it. So yeah.